Cool. So in this video, I'm going to be showing you how to use RSA using Python. So what we're going to do is we're going to write a little script to basically take what we learned in the last videos that I did in how to calculate uh, E and D and then how to encrypt and decrypt using RSA. We're not going to be using the inbuilt functions provided by Python, although I would recommend that if you're going to be using this in any actual live applications, just because it's much more efficient and it's got a lot more features that I'm going to be showing you today. But this should be a helpful learning tool in how to understand RSA a little bit better. So what are the goals? We're going to learn to write a program in Python to encrypt and decrypt using RSA. It's going to help us better understand how RSA calculations work and how it can, take place in practice. And it's also going to include randomly generating keys and prime numbers, which is a core functionality that we need for RSA. So the first thing I'm going to show you is a demonstration of what we're going to get out of this. So I've already written up a little program here. So let's take this file, rsa encryption.py, and run it. And it's going to ask us to input a message. So I'm going to write the number 14, that's my message. And that's what I want to encrypt. So here we see at the top we've generated our primitive values. So P, Q, and P times Q. These are prime numbers. Then we got our RSA public key, so we got a value of 7 for E, and our phi of n, which is P minus 1 times Q minus 1, just there. We generated a value for D as well, and then we got the actual encryption. So first off, we got our plain text message, which is the number 14. What I've done is I've encoded that using UTF-8. Then we've encrypted the message, and that's the output. And then we've encoded the decrypted message as well. And then lastly, the decrypted message itself, 14. So back to where we started. Doesn't just have to work for numbers. So in this program, because I've encoded the message, I can also use the alphabet. So I'm going to write hi. And there we go. We've encrypted the message hi. We've encoded it, encrypted the encoding. Then we've essentially decrypted the decoding or encoding, and then decrypted the message ultimately, leading us back to hi. You'll also see at the top that our values for P and Q are different. We've also got a different value for E, and obviously our D value is going to be different as well. That's because P and Q are being randomly generated, and I'm going to show you how to do that during this video. Cool. So what I've got here is just a blank Python file. I'm using Atom as my text editor, but you can use whatever you like. I'm initially going to use flat values for P and Q, but then I'll show you how to essentially upgrade it to randomize it further on. So first off, what I'm going to do is just take P equals 11. We're going to do Q equals 3, this is the example used in one of my videos. N equals P times Q. I'm going to call it R equals P minus 1 times Q minus 1, and all this should be familiar from my previous videos as well, or if you're familiar with RSA, it shouldn't be anything new here. Until we get to calculating E. Well, let's use a flat value for the time being. I'll change that later on. And then the part that everyone struggles with is D. So we've got the, I'll write it out here, E to the minus 1 mod R. That's essentially what we want to do. And we could do that in Python using the pow argument. So I'm going to say D equals pow E minus 1 R. And what that's doing is saying E to the minus 1 mod R. That's all this algorithm or equation here is doing in Python. Cool. And then that's all we need. Now we can start encrypting and decrypting. So what I'm going to do is I'm going to write two functions. I'm going to say def encrypt, and the input is M, E, and N. and I'm going to do def decrypt. And the input to that is C, D, and N. Cool. So what we want to do to encrypt, you'll remember this from my previous video, but our ciphertext, so once the text is encrypted, it becomes ciphertext, is equal to M to the power of E. So 2 asterisks is to the power of in Python, percent %n. And percent in Python, as you could probably guess, is modulo. And then for decrypt, we want plain text is equal to C to the power of D mod n as well. And this will return those values. So we want encrypt to return the ciphertext, and we want decrypt to return the plain text. And that just means if I run this, give me that at the end of it. So now we're just going to set up our main functions here, which is what you need to do in Python. Name is equal to main. Cool. And then we'll put our main function just at the top here. All right, now what do we want to do? We want to encrypt and decrypt. So I'm going to say encrypted message is equal to encrypt, and then we'll say message E N, and then we'll print that. We'll say print encrypted message encrypted message. And then we'll also want to decrypt it afterwards to show that works. So we'll say decrypted message equals decrypt, encrypted message is the input because we want our ciphertext, and then D and N are our inputs. And let's print that too. Cool, and we'll just use a static message initially. So I'm just going to say message equals 7. And let's try and run it. So we're going to say py RSA demo.py, and there we go. So our encrypted message is 13, and then we've decrypted again back to 7. So that's what we're doing here. First we're encrypting it, and then we're decrypting it back again. So that proves to us that this RSA function is working as it should be, which is great. So what we want to do next is just enrich it a little bit. So this is obviously very basic, it's static. We can choose another message, say 13, but it's always going to be the same keys that we're using here. So let's try and do something a little bit different. So firstly, let's take user input for the message. So instead of saying a flat 13, we'll say input, enter a message to encrypt. And we want to make sure it's an integer because we're performing operations on it. So we're going to say int and just wrap that. Now let's run it again. I'm going to say 7. Cool. It's done the exact same thing, but now I'm able to input a value here. And this is a good example. So here we see the encrypted message and the decrypted message are the same thing. That's very common for really small keys like this. In reality, you would use numbers that are thousands of digits long, but when you're using very small keys, there's a really high chance that you're going to get collisions like this. So that's basically why you don't use tiny keys. But just a fun little demo. And the next thing that I want to do is add a bit of variety for E. So obviously we've got E equals 3, but we may not always want to use 3. Maybe we're using big keys and 3 isn't going to be fitting anymore. So what I'm going to do first is say from math import GCD, which is greatest common divisor, and we're going to use that to find a different value for e. So what we'll do is do a for loop here. So we'll do for I in range 2 to r, and we want to check if GCD of I and r is equal to 1, then we found our e value. So e equals I. And then we want to break out of the loop if we find that. Awesome. And then let's print it. So let's print all the stuff that we got here. So at the start of our function, let's print p equals p, and then we're going to repeat that for everything that we calculated so far. Awesome. And now let's try that. Miss the colon. There we go, cool. So they print all our values, P, Q, N, R, E. We got 3 anyway. We're pretty much always going to get 3 when we're using numbers this small. And then our D equals 7. Awesome. So let's encrypt. So that's another thing. RSA encrypts in blocks. So it can only encrypt a block that is the size of or smaller than the key. So if we're using really small keys, we can only have really small messages and then encrypt loads and loads of blocks. So I've entered a number bigger than the size of our key, and it hasn't been able to figure out what to do with it. So it's given me an incorrect answer for the decrypted message. So let's do that again, but use a number within our scope. 11, we got another collision, but we successfully encrypted and decrypted the message. Again, 71 is too large, but if we go down to 17, there we go. Awesome. So now, let's try and make this even better, because obviously at the moment we're just using 11 and 3 for our P and Q. N is always the same, R is always the same. So let's improve on this a little bit. I'm not going to go through the details of this right now, but this is a function that creates a random prime number. It'll take input of the size of the number that you want in bits, and it'll give you a random prime number the size of that bit. So again, I'm not going to go through this right now, but I am going to share a GitHub page that I have that will have this code in it, so you could take a look at it yourself. If you've got any questions, then put it in the comments or DM me, I don't mind, and then we can help answer those questions. But for the time being, you just need to understand that this function creates a random prime number of a certain bit length. So in my function over here, I'm going to import that module, random prime, and then I'm going to use it. So how am I going to use it? Up here I've got P and Q. Let's just comment these out for now. And we want a different P. This time, P of random prime dot generate prime number. Oh, didn't want it in caps. Random prime dot generate prime number. There we go. And we'll give it a value of 3. And then we'll do the same thing for Q. Q equals random prime dot generate random prime number. So the random prime is the module, generate prime number is the function. It's this one here. Awesome. So now let's run this again. So this time we've got 7 and 5 as our values for P and Q. So it's generated random prime numbers of 3 bits long, so still very small keys. But now E has changed. Now it's decided 5 as the value for E. It's absolutely fine. Let's encrypt our message. There we go, 16 and 11. And now the benefit of this is it's a bit closer to the real world because we're using a different key every time. Well, not in this case, got 5 and 7 again. But let's try again. 5 and 7. Okay, let's make this a little bit bigger. Let's say 4. 13 and 11. Cool. Then what I want to do is pick a message. Let's say 13. There we go. And now if I do that again, I do 13 again, it didn't like that because again, when we're using very small numbers, it can get it wrong too. It's just another example of why I use big numbers. But I don't have that luxury because my PC is slow. Let's go for something bigger. Let's say 8. Here we go. So 193 and 239 are our prime numbers. 13. The encrypted message is 2277. Let's try it again. I have 191 and 197 as our primes. 13 again, and the encrypted message is different, which is perfect. We get a different encrypted message each time. Awesome. Now, if I want to encrypt an actual message, let's say hi, it's going to fail because it's expecting an integer. So I mentioned encoding at the very start of this video. That's exactly what we're going to do now. So first, let me just increase the size of these a little bit more. And we want to encode and decode our message. So right here, when we've got the encrypted message, before we encrypt it, let's encode it. So let's do a message encoded. And let's say that equals int, because we want an integer, from bytes, because we're taking it from the byte values themselves. Message.encode. We're going to use UTF-8, which is a very common encoding type. And byte order equals big, the very common byte order that you would normally use. Awesome. So now that we've got that, we want to move on and ensure that we are encrypting the encoded message rather than just the message itself. So we'll update our encryption input to be the message encoded rather than just the message. Now that we've done that, we also want to remove this int here because we now can accept something that isn't an integer as well. And let's run it. Let's see how it goes. So pi RSA demo, those are our numbers. Let's say A. Awesome. So now we've got our encrypted message and our decrypted message is 97. So our input's A, but our output's 97. Why is that? 97 is a UTF encoding for A. So let's make that a little bit clearer by adding another print here. And we want to say print encoded message. Message encoded. So that's what we're inputting, that's what we want to encrypt. And run it again. There we go. So our encoded message is 97, that's A encoded. Then we've encrypted it, and then decrypted it back to 97. But then I want to get back to A. I want to know what the message was, the original message. So what I want to do is then decode that. So after it's been decrypted, we want to decode that message now. So I'm going to say decrypted message decoded. And we're just going to reverse the encoding that we did before. So int 2 bytes. And we want to take the decrypted message as input. length is the length of the message, the original message that we created. The byte order is big once again. And now I want to decode with UTF-8. Awesome. And let's print that. Decrypted, decoded message. And that equals that value there. Decrypted message decoded. Cool. Let's run it. Cool. So it works for a number, our encoded message. We've encrypted it. We've decrypted it back to the original encoding. And now we've got our original message back there, 13. Let's try it with a number, or sorry, a letter, A. There we go. So 97, we've encrypted it, we've decrypted it, and then we've decoded it. There we go. So it's only going to work for 2 digits. So if I say, hey, ooh, I run that and say, hey, we got an issue. And this is because of the key link that I was talking about. Now, I could use really long keys, but it will take hours to load. It's really inefficient. And that's, I won't say it's an issue of RSA, but it's a feature of RSA that it's slow. If you're encrypting large amounts of data, you would normally use a symmetric algorithm like AES, which I'll talk about in a future video. Normally, RSA is used for encrypting small amounts of data, like keys themselves for transport and that kind of stuff. And in a real life example, you would use 1028 or 1024, I mean. So we're using 10-digit keys, and the size of numbers that we're getting is 6 digits for our key. 1024, the digits are going to be about 2000, no, about 600 digits long. So massive, massive numbers. And it takes a really long time to calculate those numbers, especially when doing it in just inefficient hardware like what I'm using here. But yeah, that's all there is to it. Before ending the video, I just want to show you this as well. So I've set up a GitHub page, which I'm going to keep all the code completely open source from all of my videos. So you can go in and take a look yourself. You can download it, play around with it, and yeah, hopefully get a bit of a better understanding than just watching me talk about stuff. So I got this folder for our first video here. We got the random prime function. I'll open that up right here. And I've also got the RSA encryption file, or a very similar one that I just used in this video as an example, and it's completely annotated, so it goes into a lot of detail about what is happening line by line. So take a look at it if you're not sure of anything, and obviously drop me a message if you want any more detail or anything else answered. I've also made it a little bit nicer in how it's outputting the information. So download this, have a play around with it, see what you think, and yeah, let me know your thoughts. And yeah, that's the end of this video. I hope that was helpful. I hope it gave you a little bit more understanding of how RSA could be used in a practical application. Again, don't do this for an actual live application because it's slow. Use the inbuilt crypto modules that Python provides. There's plenty of docs online about it that you can take a look at, but this is a really, I think, cool example of how we can use what we learned in the previous video in how to actually encrypt and decrypt stuff um, using maths with RSA. But yeah, that's it. That's all I'm going to show you today. Hope it was helpful, and yeah, I'll see you in the next video.